Hello students, in this lecture we lay emphasis upon the what is center of a group and what is the normalizer of an element of a group and what is the relation between them and derive some result based on them and solve some other problems. So let's define center of a group. So the center of group is denoted by center of group, let G is a group. The center of group G, ZG or CG or simply Z, and is defined as it is the set of all it is the set of G belonging to G which commute with all other elements of G. Set of elements of G which commutes with elements of G. So this is called center of a group. Center of a group. Now let's prove this on it. The center ZC of a group is a subgroup of G. Proof is, let definition, that ZG is center of group, G is a group, and ZG is center of group. What is this by definition? This is a set of all G belongs to G which commutes with the other elements of G. Be the center of the group. Center group is the point which commutes with all the elements. Center group is a point which commutes with all the elements of a group. So this implies the element of G, element of ZG is also the element of G. The element of G, therefore, center of a group, center of element of a group is a subset of G. Now, this all is subset of G. What is I would say? Our aim to show that this is subgroup of G. So we have to show it is non-empty, and if it will include then first and product of second also. We will apply lemma to prove this is subgroup. First, you show that this is a no ZG is non-empty. Since E into X is equal to X into E for all X into E, this implies E is belongs to ZG. So E is the any group can have more than one center. So a identity element will also act as a center of this group. Right? Now this means ZG the set of center of a group is a non-empty set of elements. So the identity element is there which commutes with all the elements of G. Now our aim is to show that ZG is a subgroup of G. So we will use lemma. We use lemma to show that ZG is a subgroup of G. For that, what we will do? We will show that if G1 and G2, if G1, G2 belongs to ZG, G1, G2 belongs to ZG, we have to show that G1, G2 inverse belongs to ZG. We are proving the result of lemma. We proved the lemma. So let us take G1, G2 belongs to ZG. The any two elements of any two elements. If they belong to ZG, means they commute with all the elements of G. G1 commute with G1 if X is any arbitrary element of G. G1X is equal to X, G2X is equal to X. So this is given. Now G1 because ZG is the subset of G, therefore G1 G2 also belongs to G. The definition of center. So this implies G1, G2, X, they are all elements of G and G is a group. Therefore, cancellation law holds true. If cancellation, so if we apply right cancellation law here, apply right cancellation G1, G1. If this is equal to this, then X G1 inverse is equal to X G2. The commute X G1 inverse is equal to G1 inverse X, and X G inverse is equal to G2 inverse X, because G1, G1, G2, and X are elements. So G and G2. Now, what to show? Our aim to show that G1, G2 inverse belongs to G. That means G1, G2 inverse commute with all the elements of X belong to G. So let's take X G1, G2 inverse. Actually holds because the elements of G is a group. So this is equal to X G1, G2 inverse. So we know that X G1 is equal to G1X. Now again associative law, G1X G2 inverse. G2 inverse is equal to G2 inverse X G2 inverse is equal to G1 X G2 inverse equal to G1 G2 inverse X. Now G1 X, we have shown that X G1 G2 inverse is equal to G1 G2 inverse of X for all X belongs to G. This implies G1 G2 inverse belongs to ZG for all G1 belongs to ZG. So this implies what this implies? This implies with the lemma shows that ZG is a subgroup. Now another theorem, G is an abelian group. Depend on it, ZG is equal to G. If G is abelian group, then ZG, all the elements of G commute with each other. So let us say given is let if and only necessary. So necessary part is going. Let G is an abelian group. If G is abelian group, this implies for all X belongs to G, XY is equal to YX. What to prove? Now this is prove that ZG is equal to G. That is ZG is subset of G and G is subset of Z. First part, since ZG is a subgroup of G, if this is given, Z is a, we have proved it earlier. Z is a subgroup of G. This implies ZG is subset. So G that implies ZG is a subset of G. First part. Now second part, we have proved G is a subset of ZG. Now let us take X belongs to G. Any element. Because G is abelian, therefore X Y is equal to YX for all X belongs to G. So this implies X commutes with all the elements of G. So X also belongs to G. X also belongs to ZG because they commute with all X belonging to set of all X belonging to G, which commute with other elements of G. So this implies G is a subset of ZG. Then A and B implies G is equal to ZG. Now sufficient part is let ZG definition ZG equal to G. Again ZG equal to G, where ZG is a subgroup of ZG is a subgroup of G. ZG is a subgroup of G. Let ZG equal to this, where Z is a subgroup of G. That is by definition, you know this subgroup of G. That is ZG is the set of those G belong to G which commutes with other elements of G. This implies because Z is equal to G, so this is equal to G. Therefore, all and G is abelian. Therefore, this implies XY is equal to YX for all X belongs to G. Z is equal to G means to all the elements. Z is equal to this, and which is equal to G given. Therefore, X belongs to G also belongs to X belongs to G, and G they are equal. So because this is abelian group, therefore X is equal to X and G. Now normalizer and centralizer of an element of group. Now let's differentiate what is central group and what is normalizer and centralizer of an element of group. Let G be a group. A belongs to G, be any element. Then the subset NA consisting of those elements of belongs to X which commute with what is centralizer of normalizer of group? It is the normalizer of an element. Suppose the element belongs to G, and centralizer normalizer of this element A is the set of those elements of G which commute with A. Is called normalizer of A or centralizer. Now our aim is to show the normalizer of an element of a group is a subgroup of G. Normalizer of an element is a of a group is a subgroup. Given to G, the element, then the centralizer of a group, normalizer of a group is the set of all X which commute with the elements of, and also is a normalizer of G. What to prove? Or is to prove N is a subgroup of G. That is, N is non-empty, and with the lemma, if xy belongs to Na, xy also belongs to Na. With that lemma, definition of Na implies Na is a subset of G. Center of a group is also subset of G, and normalizer of L is subset of G. Therefore, since E and E into A is equal to A into E, this means E into A is equal to A into E. This means Na have at least one element E, which is the identity element. Means implies Na is a non-empty subset. And non-empty, now we show we can put lemma. Let xy belongs to G. Now if x belongs to G, xy belongs to G. So let xy belongs to Na, normalizer of a group, centralizer group, the any two elements. If they belong to this, then they commute x and y belongs to A. Na means they commute with A element A of the G. Means B into x is equal to x into A into y is equal to y. This implies because the x, y, A belongs to A, therefore x inverse A belongs to A and x inverse. X inverse A is equal to x inverse, y inverse is equal to A. Now again same. Now what to do? We have to show that xy, in order to show that xy inverse belongs to Na, we have to show that xy inverse is the element of centralizer. To mean it has to commute with A. So now x A into x inverse is equal to associative law holds true. Ax is equal to xa, y inverse again the associative law. A xy inverse is equal to xy inverse, substitute value x ax a y inverse x a y inverse is equal to y inverse a, xy inverse a is equal to x inverse xy inverse a. This implies xy inverse belongs to Na, and this is it. Now let us find a relation between the center of a group and normalizer of an element of a group. Prove that center of a group G, center of a group G is the center of group G is the normalizer of an element of it. That definition of group. Center of a group G. Definition of center of group G. This is G. Center of group G is the set of all X which commute to the elements. Now, center of group G is the set of all X group G such that xg is equal to gx for all X given. That is center. This implies, what does this imply? This is true for all X belongs to Z. All X belongs to Z. What does this imply? It implies X belongs to ZG means xy is equal to yx for all X belongs to G. For all X belongs to ZG implies X belongs to ZG. This implies x is equal to gx for G belongs to G. And also if A belongs to G, belongs to G, normalizer. This is true for all x. So also now we have taken an element A belongs to G, implies x is equal to x. What does this imply? It implies x also belongs to n. We have taken x belongs to ZG and shown that x belongs to NA, implies the center of a group is a subset of the normalizer centralizer of an element. Let's prove some problems with it. If H is a subgroup of a group, then prove that for any x belongs to G, when x belongs to G, x inverse H x is equal to the set of all x inverse H x, such that set of this set for such that x belongs to for all x belongs to H is a subgroup. What's imply? H is subgroup G. Our aim is to prove that x inverse Hx is a subgroup of G for all H belongs to G and H belongs to H belongs to H and H belongs to H. How to prove this result? To show that this is a X inverse Hx is a subgroup, we have to show that number one X inverse Hx is a non-empty. Second is for all A belongs to X inverse Hx implies for all A to this A belongs to X inverse Hx. First part is X inverse Hx is a non-empty space. How to prove? Given is G is a group and X belongs to G. If G is a group, X belongs to G, then we know that G group identity element is there. So X into E is equal to E to X. If you apply left cancellation law, left cancellation of these two X inverse, because X belongs to G, G is a group, X also belongs to G. So cancellation holds in G, therefore E X inverse X is equal to E into E is equal to E is equal to X inverse EX. So and this is equal to E is equal to E comes out to be E is equal to E belongs to E is equal to X E is equal to X inverse EX. This implies E belongs to H belongs to E at the element of the group and group and subgroup is same. As we know, if E belongs to E at the G, G at the H we have this property of subgroup. So this belongs to E belongs to H inverse E implies this is monotone. It means X inverse Hx have at least one element, identity element is there, which is common with the group. Now second part is let A B belongs to X inverse Hx in any element in place. Now what kind of element they are? Let A B will be the type X inverse H1x and B type X1 inverse X inverse H2x. A is the type X inverse H1x and B is the type X inverse H2x for some H1 for some H1 and H2 belongs to H. Right? They belongs to they belongs to H. They belongs to H. Right? Now our aim is to show AB inverse belongs to X inverse HX. So let's define the product. They are element, they belongs to X, A and B belongs to X inverse HX. They have the type this type. We assume that. Now A and X belongs to G is a group. Therefore, X inverse X is for K is equal to X inverse is for KX. And X inverse to X is equal to E. H into E is equal to H. H is a subgroup of G. Therefore, H1 H2 inverse is equal to H. So just take H is a product of element of the element. They are both elements close to equal to. So let us put this correction. Now using here. Now this is equal to put their value A and B. Apply associative law here. So this product is equal to X inverse X is equal to E. E into H1 is equal to H. So H1 into H2 inverse H2 into H2 inverse H1 into H2 inverse H2 into H2 inverse H2 inverse. H2 inverse. This H2 inverse. H2, 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 H1 and H2 inverse is equal to H. So two together. So this will be, this is X inverse H2, H3, H is equal to A inverse H is. This element belongs to X inverse HX. This is what this implies. Hx inverse Hx is unity, and if A belongs to X inverse Hx, therefore A inverse also means X implies X implies X inverse Hx is subgroup. Let H be a subgroup of G, then prove that order of H is equal to order of X inverse Hx if H is a finite subset of G. We will show their order is same. Now, what is given? Given a G is blue. What is H? H is a finite subgroup G. What to prove? Our aim is to show that H and X inverse Hx have the same number of elements. For that, we have to what to do? For that, we have to show that we have a mapping from H to X inverse Hx. Let's suppose that F is a mapping from H to X inverse Hx, such that defined by f of x h is equal to x inverse hx for all x belongs to h. Now what, how you prove this result now? Now, in order to show that h and x inverse hx have the same number of elements, we will show that the mapping is 1, 1 as a result. Now, the definition. From definition, first is we will show that this is 1, 1 on 2. Definition of the mapping. For each x inverse hx belonging to this x inverse capital Hx, there exists x belongs to G such that f of x is equal to x inverse Hx. For G, this will we have a h belongs to this. G become on range of element. For each random element, we have a unique h belonging to domain. This is now our is to show this is f is 1, 1. So let us take two elements h1 and h2 belongs to h. Okay? And h is finite subgroup of G, and x belongs to G and G group. So now the mapping from f from h1. How do you show that h1? If x1 x2 belong to domain and f of x1 is equal to fx2 implies x1 plus. This is the method how will we show that the mapping is 1, 1. So we are comparing the image. We have taken x1 h1 h2 belong to domain, and if f of h1 is equal to f of h2, then the function to be this mapping to be 1, 1. H1 must be. We have already to show H1 equal to H. So now let's substitute this domain function H1 H2 going to domain H from domain set. Now their images are, what are their images? By definition, this is to x inverse h1 x and x inverse hx x inverse h1 x is equal to x inverse h2 x, because this is group and left hand this is true, implies if we left consider x is equal to e, right consider x inverse goes to the x into x is equal to e, x belongs to g group. So right consistency law implies h1 equals to, hence if h1 equals to f of h1 is equal to f is 2 implies f is 1, 1. A and B implies f is 1, 1 and 2 implies and the number of elements of h and x inverse hx are same because h and if x belongs to G. Now next question is GB and abelian group show that all elements of finite group order in G form a subgroup. Now G is abelian group. Show that all elements of finite order, all elements of finite order in G form a subgroup. G abelian group. Now what is given? Given is G is an abelian group, right? Now let us consider a subset of elements, subset which are finite. If finite, let's consider a subset of G who elements whose order is finite. So we have considered let T is the set of set belonging set of A such that even G and order is. So we have taken those elements of A whose order is finite. That is, we have supposed that to be a set T. Now, what to do? What is our aim then? What is our aim is to now our aim is to show that T is a subgroup G. Again, well, how do you show that T is a subgroup G? Again, our aim is to show T is non-empty, and if it belongs to T, A belongs to T. We are A belongs to T, closure and inverse elements. This is again lemma. Lemma. So first is we will show T is non-empty. Clearly, T is non-empty. How? For E belongs to T, or at least E also E there exists a E belongs to T whose order is 1. You know the order of identity element is 1. Now second is, so this is known. Let A and B belongs to T, then any so that order of is M, order of is M. So order is M implies A prime to B, order of is prime and B prime to B. Now I will show that now AB raised power, I will show AB is equal to B. AB is a finite number. So AB raised power Mn, AB so Mn is equal to product of power is equal to A square Mn, B square Mn, A square M is square N, A square B square N is square M. So A square M is equal to order of A is equal to M, E, and order of B is equal to N. So E to is E. This implies if A and B are a finite order, then the product is also finite. Close equal to as A belongs to T implies T subset of G, it also belongs to G. G group, it also belongs to G. The inverse also belongs to G. As we know that the order of A is M and G group, so in a group order of an element and its inverse is same. Therefore, order of the inverse is also equal to M. So the inverse also belongs to inverse is also a finite order. If it is a finite order, A inverse belongs to G is also finite order. Implies inverse T A inverse also belongs to T. T is T and inverse is therefore by lemma equal to. Now let G be a group of all 2 by 2 non-singular matrices over the reals. Find the center of G. Now you want to find the center. What is center? How to find center? Given what is given? G is a group non-singular 2 by 2 matrix. Non-singular determinant not equal to 0. And over real thing, their elements are A, B, C, D. Their elements are real. Real and non-singular determinant. Now, what to do? Now, our center of a group is center of group G is the set of G. Set G belongs to G so that G commute with all the other elements of this element. This G if this is center of this group, then this will commute with all the other elements of G. The set entities, the group entities. So for that, let us assume that we assume general element. You can write it X, Y, Z here. You can write X, Y, Z here, X, Y, Z, or whatever you want here. Let A, B, C, D or X, Y, Z you can write here. Belong to Z, G, be any element. If this is we have assumed that this is a element of the center of a center. This is center of this center. Now then it should commute. If this is element center of a group G, then it has to commute with all the elements of. So in particular, we have suppose then for convenience we suppose you can assume any 1 0 0 1 1 0 0 1 0 0 0 or other elements also. You can see whether there is number also. Let us suppose this element commute with these two elements of G. The element is 1 0 and the 2 by 2 matrix non-singular 2 by 2 all the elements are given. So they also belong to G, this also belongs to G, this one. If it commutes with the, if this element commutes with the, then A, this into first is equal to A, B is equal to B, A is equal to, multiply them, 2 by 6 equal, if the corresponding coefficient equal, find out the ABCD from both the sets, and when we generalize both the sets for, uh, uh, we find that, hence we find that C is equal to 0, B is equal to 0, and A comes out equal to D. So what for which form this element took in Z, if it belongs to Z, ZG? It takes the form A 0 0. So this is center of, hence ZA ZG or ZCG is a set of elements whose diagonal elements are equal. Diagonal number non-zero is real number, and non-diagonal elements are 0. Is called the center of this equal to non-zero set of equal to non-zero numbers. Right? Thank you very much.